Yeah, micro working. So yeah, just a bit of an outline as to what I'm going to be doing. Who am I and why am I doing this? And I'm going to go over a bit of x86 exploitation just to get you in the mindset of what it is like to actually do exploit development. Then going to go over Android and its actual internals and take a look at the actual application binary interface, the assembly, the registers, whatnot. And then I'm going to actually take a look at exploiting. Unfortunately, is the microphone working? I'm fine. Unfortunately, my demo died on me, so I typed it out instead. And then, going to talk about some mitigations that ARM have implemented. So firstly, an introduction. I am John Doe, as some may call me. I work at BAE Systems as a security researcher. Been up there for the past 2-3 months. I'm also a university student studying part-time. Starting my second year, currently studying cybersecurity. And then I also play CTFs in my spare time and have been doing that for the past 3 to 4 years. Started out with x86 reversing, moved on to exploit development a year after that in the x86, looking at stack heap, and then a bit of the kernel exploitation. And then I moved on to Android versing and Android exploitation in the last 1 or 2 years. So why am I actually doing this? In my research, there is only one conference talk that I've found which is exploiting memory corruptions in an Android context. You got the links there, and you got a couple of more talks exploiting ARM binaries. So there's just not enough awareness of this that is out on the public internet. And I recommend, a lot of people check that out. There is the link there. That's the 2013. So that's a 32-bit, context, 32-bit ARM. And we're now running, ARM 64 was introduced in 2014. So there's just, there's just not any research done. Let's take a bit of a look at exploitation, just giving us a bit of a background. So normal x86 64 exploitation normally starts out with a buffer overflow or a format string or some way where you get an out of bounds read or write. One of the ways which, once you've found that vulnerability, when you start to exploit it, how would you actually get code execution? That's what we're here for. The main way was shellcode, executing or compiling assembly into machine code in which you could then chuck that into the binary. Just run your shellcode. It will get you out reverse shell, get you out open files, whatever. That was prevented with non-executable, which is a page table mitigation. Which essentially says all your pages, so a page is your stack, your libc, regions in the binary, that basically says this page can either be read and writable or read and executable. So this means that you're not able to write shellcode onto the stack and then execute it, just because that will break the NX. So how do we get around that? We went to ROP, return-orientated programming. That's now turned into, some extra ones are JOP and COP, jump and call orientated programming. And that is chaining together assembly instructions with a return or jump to essentially get code execution. And these ROP gadgets are used in any ret to X, your ret to libc. So that's jumping or pushing bin sh onto the stack, and then jumping to the system call. You've got ret to CSU, which is using the Dunder libc CSU init, which is defined at the start of every C binary. There's a bunch of SIG-ROPs and everything else. So how was that mitigated? Not quite mitigated, but how was it made harder? We introduced PI, position independent executable, or PIC, position independent code, which essentially defines a page as a base, and then every function in a binary is at an offset to that base. And so that's effectively how pi works. How do we defeat pi and ASLR? ASLR does the same thing. Pi is just for the binary. ASLR is for all the other pages: stack, heap, libc, LD, Linux. So yeah, how do we defeat those? It's a bit of a cat and mouse game, as you can guys see, but how do we defeat those? It's leaking addresses, which we can then calculate offsets to the base of the page, and then we can find any other offset that we want. So yeah, let's take a look at Android. So what actually is an APK? An APK is essentially a zip file. There's a bit of a bash script up there, but that essentially tells you how many each file extension there are. So you have an Android resource file, which contains the identification or IDs of every single function in an app, as well as anything in an app. You then get your dex files, which are your bytecode. So I forgot to mention, Java is written in APKs. Android applications are written in Java or Kotlin, and they are then compiled down to your bytecode. So the dex is your bytecoded version of that. Your MF file, your manifest file. When publishing an APK, you have to sign it, signed with the RSA key down there, the extension. And that manifest file contains a hash of every single file in the APK and its hash. So when people want to recreate or add extensions to your APK, they have to sign it, but those hashes won't align effectively. And then, we get a couple of others. The big ones are PNGs and XML files. Every file in your Android phone is an XML file. Every, view, rather, is an XML file. So that's effectively what we're working with. And when reversing an Android application, you want to look for the Android manifest XML file. This contains the entry point for when an Android app starts. As you see there, it's commonly your com/company name /app name /main activity, and that will show you any broadcast activities, any intents that an Android has, ways to interact with that Android app, not from the user. There's also the strings. You get the two paths there. The top path is from Android version, I think SDK up to SDK 24, which is Android 5, 6, I believe. And then the bottom location in your resources.arc resource is where strings are now located. And then there's also this folder in /res/lib/star. Lib stands for library, and that picture didn't come out well. Reslib contains shared object files. Again, something I forgot to mention. Android apps, whilst using Java or Kotlin, you can also interface with them through C and C++ and assembly through the JNI, the Java Native Interface. And that allows you, to do anything low level that you want, threading, opening files, whatever. So these have to be compiled and then brought in with the app. So these are stored in your res/lib/star.so files. So that's a bit of brief about that. So let's actually dive in to what an SO file contains. This is the bit which people don't like. This is the bit which people are scared to get into reverse engineering, because we take a look at assembly, we take a look at registers. It's the bit that scares people. ARM have done a very, very good thing of having an actual web page for their documentation. You take a look at Intel's documentation, and that is just a 5,000 page PDF, which you do not want to read through. AMD has something similar. I think theirs is a web page, but it's not the most accessible. No hate to Intel and AMD, by the way, but ARM just have this absolutely lovely way of searching through this website. So let's actually get a look at the registers involved. So as you can see there, I've put the x86-64, if you know that, those registers there. So yeah, you get your X0 to X30 registers. Those are your general purpose registers, and those correlate to your RAX to RDX, R8 to R15 registers in the 64-bit context. So the first 8 registers, X0 to X7, are the registers that hold arguments to functions. If you have more than 8 arguments, you put them on the stack. And yeah, as you can see, that correlates to those registers up in there. I can never remember them, which order they go in. So yeah, put them up on there. X29 is your frame pointer. So in x86, X29. So in x86-64, you've got your stack frames for defining functions. So this is essentially what the X29 register holds. So yeah, as you can see, it's the RBP register. You get your X30 register, which isn't really known in the x86-64 world, and that is what's known as the link register. And the link register holds, when you want to jump to a function, essentially this X30 register will be it will be populated with the address of where your saved RBP in x86 world, effectively. So when you want to jump to functions, that is where you want to be looking for. That is where program is going to be redirected to in the X30 register. You then get your stack pointer, also when used in assembly code, known as the 0 register. And yeah, that again correlates similar to the stack frame with your RBP, and that's used there. Finally, you get your program counter, same as x86, and then your current program status register or application program status register. And again, x86 just holds the flags. Something interesting in ARM, specifically 64-bit, is that the ARM registers can only access, the ARM assembly can only access 64-bit and 32-bit parts of registers. It cannot access 16 or 8 bits as you see in the x86 world. If you do want to do that, you can't. That's in, the 32-bit version of ARM. So you're only able to access 64 and 32, denoted by X for your 64-bit and W for your 32-bit. Yay, assembly. So yeah, as you can see, we have a bit of a different relation, or bit of a different layout to x86 with ARM. ARM usually takes 3 registers or 3 operands for an opcode and the instruction. The move and compare. Saying that, I've just put a couple of 2. But yeah, there's 2 or 3 registers involved. The normal way of thinking is the first operand holds the result of the instruction occurred on the second and third register. So as you can see, you get move, compare, LDR, load, register, and then it's got a couple of arguments, as you see with at the top you get the mnemonics, and then the S, that stands for sign, and then the conditions. So down in that LDR bit, those are your conditions. You can have a signed byte, You can have a signed half word, or 2 bytes, or you can have a signed word, which is 4 bytes. And of course, you can remove those S's for unsigned. There is also this concept of indexing, taking a look at the next 2 load register assembly codes. Well, yeah, it pretty much tells you there in the purpose what they are doing, but essentially you have post indexing, which is that top one there, which is saying add 8 to the X1 register and then perform some functionality, load it into X0. You can have normal intermediate indexing, which is your standard load X0 and X1 into X0, and then add 8 to X1. The store assembly code, it performs the load, but in the opposite direction of which way around the registers are. And you can also store a pair of registers. So you commonly see this function down there. At the beginning of functions, you're going to store the pair of x29 into the stack pointer, and then x30 into stack pointer plus 8. You can also add a comma and then a constant after the stack pointer, so that you can define where that second register is going to be pointed to or stored. And then, yeah, as with x86, you get your jumps. In ARM, we have branches. BR branch to X0, BL branch to a label, BL printf, for example. And there's a couple of others. Take a look at the documentation, ARM documentation for more. And then there's also the ret instruction, which, yeah, as I was talking about the link register, it's going to jump to the what the X30 register holds. A couple of more. So these are more your addition, subtraction, your logical, mathematical instructions. The LSL means logical shift left and logical shift right. And yeah, as you can kind of see, those are just the instructions, add, sub, and or negative, XOR, NOP, reverse, which quite literally takes the bytes on the right of a register, plonks them to the left. And then, yeah, you can also rotate right for some odd reason. However much you want of a register. So when actually reversing, I talked about the functions and the sub. So what do we actually see? So there is this, we want to first allocate some space for our function, as we see in the Intel, normally decrement the stack pointer by a constant, how many registers you want to store on there. We're then going to store these x29 and x30 registers, the link register and frame register, onto the stack pointer just to save them. And then, yeah, we're just going to perform all our other functions. And yeah, on the right-hand side is just a bit more where you've got a couple more variables used. And then in your epilog, when you want to exit the function, you can load a pair of registers, x29, x30. Load the stack pointer into x29 and the stack pointer plus 8 into x30. And then, yeah, essentially close the stack frame, adding 16 to your stack pointer and then returning. As you can see on the right, you've got a similar thing. This time there's just a check with stack pointers, which I didn't mention at the start, but yeah, you get your stack canaries, essentially checking if there is a buffer overflow. Yeah. Just jumping a bit abroad from an application level, in Android, in x86, we have the ring model of ring 0 being the user space, the space where applications can run. And then we got ring 1 and 2, which is where device drivers are able to run their code. And then we have ring 3, which is for kernel operations. So, and that's just, degrees of separation, just separating out your memory. So we have a similar thing in ARM context. We have the exception level 0. So any time that an exception is raised, whether that be anything that goes wrong, there's been a buffer overflow, some address has gone wrong, it goes into one of these exceptions. And so, so you get your exception level 0 is your ring 0 where user space applications happen. You get your exception level 1, which is where the kernel will operate. Then you get your exception level 2, the hypervisor. And then you also get exception level 3, which is your firmware. And again, just degrees of separation. Most people know that in Android, the Android is built off the Linux kernel, a bit more hardened with a bit more SE Linux. And it separates its applications out into its own user. So it's got its own user ID and group ID. But this is just saying that it actually goes a bit more further when you dive deep down into the actual levels of privileges. So let's go a bit more back on track, back to exploitation. So when you want to reverse an Android app, you want to get it from the target device that you're running it on. You might get it from the Google Play Store. You might get it from, it might be provided to you from you. It might be from a shady link from the internet, looking at you, APK tool, APK droid even. Or you can, when downloaded on a target device on your phone, on the IoT, you can pull it with ADB, Android Debug Bridge. And that's just the commands up there that you can use to pull an APK. Once you've actually got it, if it's an APK, we can then extract it. We can either through unzip, or we can use APK tool, which does a bit more than unzip. It unzips and converts the DEX bytecode into actual Java code, so it's nice and easy for us to read. And then once we've actually got the contents, we can then start reversing. Smiley is assembly in x86 ways. And we can start decompiling using JARDEX or any other decompiler, and we can also use decompile ELF or shared object files through Ghidra, IDA-Pro, Hexarrays, or whatever. So this was the bit where my demo wasn't working. I was going to show you how to perform a ROP chain on an actual target device, although for some reason it wasn't working, some stack registers. So this is the essence of what an actual attack would look like. Let's say that you had a C binary that, uses the gets function because that's insecure, it's not size checked. We can perform some buffer overflow. We can essentially provide our padding up to where we want to overflow the buffer. We then want to load into x0 our first argument to a function, the bin sh pointer, if you want to execute system bin sh, for example. And then, we're going to do this very similar thing. We're going to load the pointer to system into the x30 register, and then just watch our shellcode run and hopefully get a shell. Although it's never as easy as that. You don't just get gadgets handed to you like that, like your LDR X0 to the stack pointer. As with, sigrop and normal rop on, ret CSU, for example, in your actual binary, there are very limited registers, so sometimes you have to be creative in your rop chains. So that was that. I was going to show, actually reversing, but it's just a bit of a pain. Let's talk, now that we've actually exploited, what is ARM actually doing to prevent these exploits, vulnerabilities from happening. So first off, as with x86, we get xn, your wrong way around, nx, which is your non-executable pages. In ARM, we get xn, execute never. And that can be broken down into uxn, your user privilege, execute never, which happens in the E exception level 0, your user space applications, and then it can be also broken down into kind of your kernel area of pxn, privileged execute never. This is just a bit more from how that actually works from the actual ARM documentation. They've actually documented how they are preventing, which is actually really cool. You don't see that in Intel. You can read that. I think the main point was location writable in exception level 0 in your user space is never executable at the kernel level, regardless of what the control bits are set to and configured. So we then get our ROP. How is ARM mitigating against ROP chains? They're introducing something called PAC, or Pointer Authentication Code. Some of you keeping up with security might have heard about the most recent Pac-Man attack, where some researchers from an institution in America essentially defeated this pointer authentication code on the Apple M1 chips, which is really interesting, really good read, would recommend it. How does pointer authentication code work? Registers, actually use, you've got 64 bits to work with. Registers only use 52 bits of that 64 space. And so what ARM have done is they have essentially realized this and said, okay, can we store a signature defined by this pointer authentication code, defined by a couple of keys and how we do stuff? We're going to store those in the 52 to 64 bits of a register. As you get that big wall of text there, essentially what that's doing is that means that for when you leak addresses in the in the binary, you get your gadgets, but then you also need to try and find where your gadget is for this signature, how this function's actually been signed. So something that we haven't quite seen on Intel, would be quite cool to see it. So that is how ROP is being mitigated. And I mentioned JOP, jump orientated programming. How is ARM mitigating against that? It uses branch target instructions, essentially landing pads for when functions want to jump to another function. As with the trampoline, if you're trying to jump from one trampoline to another, that's all fine. If you jump from one trampoline and fall on your face and hit the floor, that's not fine. So that's what these landing pads are. So at the start of every function, there is this new opcode called BTI. And whenever a jump instruction is called, the next assembly instruction to be hit should be that BTI. If that isn't, then it's going to generate an exception, and just crash your program. And we've seen this in Intel, actually. This is what Intel are integrating into their CET, control flow enforcement technology. I believe it's with their shadow stacks, where they're trying to put an end branch at the top of every function. So whenever a function is returned to or called, then it should hit this end branch function. If it can't, then it fails. And so, yeah. And then how are these? So this mitigations aren't currently compiled by default. You have to add a flag when compiling with GCC or LLVM or Clang or whatever. And yeah, so you can provide this argument end branch protection, and you can provide the arguments of one of many. You want to either pack ret. So something that I didn't mention about a pack, I mentioned about the keys actually. You have 5 different keys. You have a general use key. You have an application key, A instruction key, B application key, and B the B, A's and B's. So essentially this is defining which key is used to sign those instructions. And then, yeah, you've also got the leaf function. What a leaf function is pretty much like a lambda in your high-level languages. It's essentially an anonymous function which doesn't have a stack frame pointed to it. That's essentially what a leaf function is, even. Yeah, so that's introduced using pack. You then got your BTI, just standard branch instructions, your landing pads, and then you can compile with both using the standard, nice and easy to remember, or you can have no instructions, no protection, sorry. And yeah, like I said at the start, that's default. And yeah, something else that ARM documents in their ARM documents is how on earth do we prevent against buffer over attacks and use after freeze? Essentially things that are user controlled as opposed to, oh, we've just got a gets function that just runs. They introduced this thing called memory tagging. And what that is similar to the pack pointer authentication code. It's signing addresses using a key. And yeah, it pretty much says on the slide there. But yeah, so that is what ARM is implementing. And then, yeah, thank you very much. Does anyone have any questions? Any good reading suggestions? The ARM documentation. Yeah. So, over in my references, Azeria Labs is a really good place that introduces you into ARM 32-bit. So yeah, that does need to get you updated. But yeah, Azeria Labs is really good. They've got everything that I've essentially talked about. I've not quite copied directly, but I've used a lot of their knowledge. They also have some labs which you can use to practice and, yeah, also exploit. And yeah, if you just do a Google search of, yeah, ARM assembly, ARM programming, there are loads of there are a decent amount of, not loads, but there's a decent amount of resources out on the web which you can use. Yeah. No, so that's one of the things. Yeah, so the question was, how do we defeat pi and ASLR in this ROP chain here? This is essentially boilerplate code. It's not. This is what you want to achieve. So like I mentioned about like your ROP chaining, you don't get just these gadgets, this LDR, X30, see your stack pointer them, right? You don't get that in the normal world. So defeating pi and ASLR is more application specific. You want to cause a leak either by, if you have a format strings using printf, there's a format string vulnerability there, you can start read. You got your out of bounds reads, all that kind of thing. So this doesn't explain it here, but it's application specific. You see it in a lot of CTF binary exploitation challenges, where, they do get you to leak ASLR, or they leak it for you, for example. Any more? Thank you very much.